This video is a brief tutorial on how to draw Lewis structures. The steps described may be slightly different than the method that you learned in general chemistry, but don't worry, there are multiple approaches that can be taken to come up with the correct Lewis structure. We draw a Lewis structure when we are given a molecular formula and we want to determine how the atoms are connected and how the electrons are distributed. In this case, I'll go through the example of drawing the Lewis structure for CO2. The first step is to count up the valence electrons. Carbon has 4, which we can easily remember because it is in the fourth column of the periodic table. Oxygen has 6. So the total number of valence electrons that we need to include in our structure is 4 plus 6 plus 6, or 16. If our formula included a charge, we would need to add or subtract electrons, but in this case there is no charge. Next, we need to establish connectivity by making single bonds between the atoms. This can sometimes be the trickiest step. However, a couple of tips to make this easier are to arrange the atoms as symmetrically as possible and to put hydrogens and more electronegative elements on the outside. So in this case, we'll put the carbon in the middle and the more electronegative oxygens on either side of the carbon. This follows both guidelines, as the atoms are now arranged symmetrically and the more electronegative oxygens are on the outside. Remember that a single covalent bond is made up of 2 shared electrons. In a Lewis structure, this bond would be represented by 2 dots. In a Kekulé structure, the bond is shown as a line. Either one is correct. In organic chemistry, we generally draw bonds as lines and often still call the structures Lewis structures. In the third step, we can complete the octet for each of the outside oxygen atoms. For the oxygen on the right, the 2 electrons that make up the bond between oxygen and carbon count towards oxygen's octet. So we need to add 6 more electrons, or we could say 3 lone pairs, around this oxygen to complete its octet. We'll then do the same thing for the oxygen on the other side. Now, let's count up the electrons we've used so far and compare them to the total number of valence electrons we have available. Currently, we have 12 electrons in lone pairs and 4 electrons in bonds, giving us 16 electrons that we've used so far. 16 was the number that we started with, so at this point we've used up all of our available electrons. We already know our outer oxygens have a full octet because we did that in the previous step. So next let's look at the other atoms, which in this case is just our central carbon, to see if it has an octet too. In this case, the 4 bonding electrons count toward the octet of carbon. This means that our carbon still needs 4 more electrons to fill its octet. Since we don't have any electrons left to use, we'll have to share some of the electrons currently around each oxygen with carbon to make double bonds. Since carbon needs 4 more electrons, we'll take 1 lone pair from each oxygen to make it a bonding pair, giving us 2 double bonds. Now every atom in the structure has a full octet, and we have the correct Lewis structure for CO2. Here are a couple more example problems. The first formula we're given is an example of what's called a condensed structure. It's written in such a way as to indicate which atoms are attached to each other. These hydrogens written after the C are attached to it, while these hydrogens written after the N are attached to the nitrogen. We will see shortly how this can help us draw Lewis structures much more quickly and without having to go through all of the steps, but this time we'll go through all of the steps again. So first, to count up our valence electrons, we have 4 from carbon, 5 from nitrogen, and 1 from each hydrogen, giving us 14 total. Next, we'll draw our single bond framework, attaching our 3 hydrogens around the carbon. Then we'll connect the carbon and nitrogen, and attach 2 hydrogens to the nitrogen. In doing that, we've made 6 bonds, so we've used 12 electrons. That means we have 2 more to use. Remember that hydrogen follows the duet rule, and so it only needs 2 electrons to be satisfied. In our structure so far, each hydrogen has 2 bonding electrons and the carbon is also surrounded by 8 bonding electrons. However, we can see that nitrogen does not have a complete octet. So, we can add a lone pair to nitrogen to get our final structure. For the next example, we have 1 electron from hydrogen, 4 from carbon, 6 from each oxygen, plus 1 because of the negative charge. That means we have 18 valence electrons to work with. We'll start with our carbon in the middle and arrange the other atoms around the outside. Completing the octets on each oxygen, we've used 18 electrons, 6 for bonds and 12 for lone pairs. But as in the first example, our central carbon does not have a complete octet. It needs 2 more electrons. So we'll move a lone pair from one of our oxygens to form a double bond. Which oxygen has the double bond to carbon does not matter. We'll come back to this later on when we talk about resonance. However, just as a reminder, if we draw the Lewis structure, showing the carbon double bonded to the other oxygen, then these two structures are considered resonance structures of one another. Finally, as I mentioned before, in organic chemistry we are almost always given condensed structures rather than molecular formulas. We also see the same elements again and again: carbon, hydrogen, oxygen, nitrogen, and the halogens, with sometimes a sulfur or a phosphorus thrown in. Because carbon has 4 valence electrons, it always forms 4 bonds in a stable structure. Likewise, nitrogen forms 3 bonds, oxygen forms 2, and hydrogen and the halogens form 1. These guidelines, and a few exceptions that we'll see at certain points, are provided in a handout called Common Bonding Situations in Organic Chemistry. Since we're given condensed structures and we know how many bonds each atom will form, we don't need to count out all of the valence electrons, which can get very tedious in a larger structure like the one shown here. Instead, we can fill in the bonding framework and then make sure each atom has the correct number of bonds. In this example, starting from the left, the first carbon has 3 hydrogens attached to it. It's then attached to the next carbon, which has 2 hydrogens attached. We can keep going down the chain. Now we see these 2 carbons in the middle only have 3 bonds each. We can remedy this problem by connecting the 2 carbons by a double bond instead of a single bond. At the other end, the oxygen has 2 bonds, which is its preferred bonding situation. However, we need to fill in missing lone pair electrons to complete its octet. Note that in organic chemistry, the lone pairs are sometimes not shown, but it's always a good idea to draw them in for yourself.